All right, so now that we have a general idea of what reaction rate is and some of the factors that can lead to differences in rates of reaction, as well as the collision theory, let's take a look at how we can measure the progress of a reaction and then also how we can express the rate or the speed of a reaction. We'll take a look, first of all, at what's known as the average reaction rate. And let's just assume, just for simplicity's sake, we're looking at a simple reaction where reactant A, is being converted into product B. Okay, so remember now, A on the left side, that's the reactant, and then B on the right side, the product. And if I were to, for instance, plot or chart the concentration or the amount of A and B over the course of time, we can see something very interesting. So if I plot time here, let's just say seconds on the x-axis, and then we have concentration of A or B on the y-axis, we can see something very interesting. So let's say we'll put A in purple, okay, and then B is in green. So initially, before we allow this reaction to happen, all we have present, right, is just A, right? Because that's what we're starting off with. So purple. All we have is just A. So at the beginning, our concentration of A is very high. Whereas at the beginning, before we allow A to be converted to B, we don't have any B, right? So the concentration of B is actually 0. As we allow this reaction to proceed, if we hit go, for instance, we allow this reaction to happen, what we will notice is as A is being converted to B, the concentration of A is going to slowly decrease as it is being converted into B, right? So the concentration is going to go down, 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 down. And guess what happens simultaneously to the concentration of B, the product? Well, at the beginning, we don't have any B, but as A is converted to B, guess what? The concentration of B starts to increase. Okay, so the concentration of B goes up as time passes. The concentration of A goes down as time passes as well. So the way that we can represent that process with respect to, from the frame of reference of either the reactant or the product, is by writing an equation or writing a relationship between the rate or the speed and the concentrations of each of those, the reactant or the product, with respect to time, the change in time for that change to happen in the concentration of A or B. So we can say, for example, with respect to A, and A's our purple, so WRT is my abbreviation for with respect to, and that's concerning this thing or that thing. So with respect to A, right, we can say that the rate of the reaction, right, is simply equal to the change in the concentration of A. So the change in anything is this triangle. This means delta. That stands for delta. And it means change in something. In this case, it's the change in the concentration of A. And then the time that it takes for that change to happen, which would be the delta T, change in time. Right. So what you will notice also is that, yes, the concentration of A is changing. It is decreasing, right, as time progresses. So we actually need to put a negative sign here to account for that, right? That tells us that that particular thing, whatever it is reacting to the product, that is actually going down as time passes. We can look at this with respect to B as well. Okay, so the rate of the reaction is the change in the concentration of B, and as we know now, the concentration of B increases as time passes, divided by the change in time, or the time that it takes for that change to actually occur, right? So we've just expressed the rate of this particular generic equation in terms of the concentration of A, and also in terms of the concentration of B, the reactant and the product. So a couple of things to consider when we look at reaction rates or speeds of chemical reaction. Rates are always positive. You can have a negative rate. So that's why we actually need to include this negative sign here to actually convert our change in the concentration of A from a negative value to a positive value. And I'm going to explain this here in a second. So if I decide for A, for example, to pick to determine the rate of the reaction from time equals 0 to, let's say, time equals 10 seconds. Okay, so I'm picking this data point here, and then I'm picking this data point right about there. Right, I can measure, I can record whatever the concentration is to start with, and I can also record what the concentration is to end with, and that is going to be my delta A, right? The change in concentration of A would be, if I label these as 0.1 and then 0.2, right? The delta A here, meaning concentration of A would be the final where I end up, which would be 2 minus 1. And as you can imagine, right, 2 is a smaller value than 1. So this is going to lead to a negative value, okay, which is why we need to include the sign to change it from a negative to a positive value. And then the change in time here, delta t, right, is simply whatever time we end up with, which is 10, minus our initial time that we started with is 0. So the delta t there is 10 minus 0, which is 10, in this case, seconds. Okay, so that's how we can use that graph or tables, for example, to calculate that rate of the reaction. I can also look at it in terms of B. Okay, so the change delta concentration of B here. If I select the initial concentration of B, which is down here, we'll call that 1. Then the final concentration of B, let's say it's right up here as well. So that's going to be 2. Well, then the change in concentration of B would be where I end up, which is value 2 minus my initial value, right? Obviously now, 2 is a bigger number than 1, right? 1 being 0 over here. This is going to be a positive value. Okay, and then our change in time is the same change in time. We end up at, let's say 10 seconds, 0. Okay, so that 10 seconds would be our delta t. So if I divide positive by positive, that gives me a positive value. Our rate is positive. Okay, so just be aware of that when you see that negative sign in these rate reactions or rate equations, especially when it comes to the reactant, because the reactant's concentration is decreasing, you stick the negative sign in there to ensure that the rate is actually a positive value rather than a negative one. We can monitor the concentrations if it's very difficult or if it's challenging to determine the concentrations, the reactants, or the product. We can use different techniques. Okay, so we can monitor concentrations of reactants or products over time. Using different techniques, we can sample we can take samples out of the reaction mixture at different times, and we can determine the concentration of the reactants or products several different ways. If your reaction has a certain color associated with it, right, we can use a spectrophotometer, for instance, very similar to the one that you either have used or you will be using in the lab. So we can use a spectrophotometer or just simply a colorimeter. Okay, and the darker the color, the higher the concentration, and you can do a Beer's law, for example, plot to actually determine the concentration experimentally. If there are gases present, we can use a gas measuring device like a manometer. If there are charged species, positive, negative ions, for instance, that are being produced, we can measure the conductance. There's a variety of things. I'm going to say dot, dot, dot. There are a variety of techniques that we can use to monitor the concentration of reactants or products over time. We can plot them on a graph, and we can plug them into our equations to determine the rate in such a way. Now, the thing to note about this particular example is that what we get when we use this technique is what we end up determining what's known as the average reaction rate, right? And then this is over a particular time period, whether it's in this case 10 seconds, okay, maybe an hour, maybe a day, maybe 3 seconds, doesn't matter. This technique particularly gives us an average rate of a reaction. So if we take a look at a specific example now, rather than a generic A turning into B. So here we have the reaction between bromine, Br2, which is a diatomic molecule, aqueous solution, reacting with, this looks like methanoic acid or formic acid. To produce our products, we get the bromide ion, we get protons, and then we get CO2 gas. We can write the average rate equation for this in terms of, or with respect to, so the rate with respect to one of the reactants, bromine now, you can say is rate equal to the change in the concentration of bromine, Br2, over the change in time, delta T. And then because bromine is a reactant, okay, we need to have that negative sign in front. Okay, the change in anything, delta anything, is always the final minus the initial. Okay, so that's really, really important that you remember that. We saw this back in Gen Chem 1 when we looked at Hess's law and a bunch of other types of reactions, thermochemistry as well. The change in anything, so delta, let's say X, right, would be X final minus X initial. It's always final minus initial, right? Where we end up minus where we started. So if I look at the change in delta, sorry, the change in bromine, right? That would be whatever the concentration of bromine was finally. So say the final concentration minus concentration of bromine initially. Okay, and then that's divided by the change in time. So T final minus T initial. And remember, bromine is a Br2 is a reactant, so we need a negative sign in front. So this may look slightly better than the equation that's shown here. It's the exact same thing, but just written in a slightly different way. Hopefully it's easier to interpret. So this is the average rate that we can express. And in this particular reaction, your bromine, as you may know, bromine is a brownish, sort of has a brownish color associated with it. So it starts off very brown. And then as time progresses, going from left to right, as time passes, the color fades because the bromine is being used up. And if there's less bromine, guess what? The color is going to become less and less intense. So we can actually use a colorimeter, for instance, to monitor the concentration of bromine over the course of time. And we can plot that data, or we can collect a bunch of data, on a chart, for instance, and we can use that now to determine or to calculate the average rate of this reaction. So let's say, for instance, so for example, we're asked to calculate the average rate of this reaction over the first 50 seconds. Okay, so I have a bunch of data here. I have time here on the in this column. I have the concentration of bromine on the second column, right? So if I were to calculate the rate of this reaction with respect to bromine, so as a key here with respect to Br2, right? I can use the information from the table. So I'm looking at the first 50 seconds. So that would be, let's see, over here, I'm looking at. Okay, and I'm starting at time 0, going to 50. Okay, so I have, in this case, my T My time initial, that's starting at the beginning, is 0 seconds. My final, T final, here is 50 seconds, 50.0. That's where I'm ending. And I also have my concentrations of bromine, right? So the concentration of Br2 initially is, what is that, 0.0120 molar, and then the concentration of bromine at the end. And the end here is after 50 seconds, right? So just over the first 50 seconds. So I match that up, and that's 0.0101 molar. I can then take these and I can stick it into my general or generic equation that I had given up here, right? So if I were to substitute, so the rate equals negative, and then Br2 final, so we have 0.0101 minus Br2 initial, so final minus initial 0.0120, and then that's molar divided by the change in time, so 2 final is 50. 0.0 minus 0.0, and then that's seconds. So obviously, that's going to give me 50 seconds in the denominator. And then whatever I get in the numerator, I divide those by each other, and I end up with a positive value because the number in parentheses ends up being negative. We take negative sign. So we end up with 3.80 times 10 to the negative 5. Then our unit here, molar per second, or molarity per second. And so you can calculate the rate over the first 50 seconds. We could also calculate the rate over the first 100 seconds by a similar manner. We just plug in those values. And then what we find is that the rate over the first 100 seconds is 3.54 times 10 to the minus 5 molar per second. And as we just found, the rate over the first 50 seconds was 3.80 times 10 to the negative 5 molar per second. So what you will see is that the rate, the average rate, are not the same. Okay, and actually what we see is that as time passes, what happens to the rate? Well, the rate actually, right, actually goes down. Well, we didn't, this is from a different but we just calculated here from our two examples over the first 50 versus over the first 100 seconds, right? The rate actually decreases. Right? And that's the average rate. Right? So as time passes, the average rate of the reaction goes down.